We've gone over how a single neuron model can be used to make predictions and help you solve a problem. The computation that it does, which is to take the weighted sum of inputs, add a bias, and feed this through an activation function, is the same computation of single neurons in large neural networks with millions of neurons. It's also the same computation of single neurons when the input has millions of dimensions, which is often the case for modern deep learning problems. So it's always taking weighted sum of inputs, add a bias, and feeding the sum through an activation function. Remember, though, that the activation function can take on many forms. In practice, for modern deep learning networks, often the activation function used is something like the rectified linear unit, which makes it easier for learning. The single neuron model has served you pretty well, but there are limitations to what it can do. I'm going to show you an example of a situation where the single neuron model will not be able to help you. Say you're playing poker with Rob and you see the following expression: a very deeply red face color intensity and a very deeply frowny mouth. Your original two-dimensional perceptron model had said that the greater the color intensity and the more frowny the mouth angle, this meant that Rob should be telling the truth. But it turns out he's bluffing. And this means that while it seems true that the less smiley and more intensely red Rob tends to be, the less likely he was to be bluffing up to a certain point, until it gets to the extreme of him being very red with a very deep frown, and then all of a sudden, he's bluffing. This phenomenon where the model outputs values that don't correspond monotonically with data values, this is known as nonlinearity. So to model this situation, we're going to need another line on the plot to fully separate all truth examples from bluffs. Except for now we have a problem, because a single neuron perceptron can only represent a single line, and so it can no longer represent the situation where we need two lines to separate truth from bluff data. We're going to need more than one neuron to represent this, and in the next lecture we're going to go over why this is the case and how this can be done.